as usual, please do, we encourage you to find these slides because you might want to have the questions up for the breakout rooms and stuff like that. You can find them at bit.ly/MCCE links is the whole Praxis participants folder, the Praxis teachers folder. And then within that, of course, you have the fall folder. And then today's date, there's that parking lot. We encourage you to put in your questions on that parking lot as we're presenting today. We'll try to look at it right at the end to answer any questions, as well as we've been doing that during the weeks. And this is always a very useful reference to have that Praxis study guide. So what are computing systems? So what does that even mean? Well, the big picture, you can talk about computing systems as sort of two categories. We'll first look at the systems working inside of a computer, like the hardware system and the software system, and the special case of one type of software, the operating system. But computing systems also deals with more than one computer working together. And so we'll talk in this section about the Internet of Things and how that is more than one computer working together. We'll talk about the cloud. And of course, networks are exactly that definition, more than one computer working together, connected to each other, exchanging information. And so more of that will be in part 2 later on today. So here's the outline. So I know that's probably pretty small print. I apologize for that. But this comes directly again from the ETS outline and test guide for computing systems. Part A is the part we're looking at in this presentation. You should know that about operating systems here for number 1. Be familiar with computing systems embedded in everyday objects like the Internet of Things, ATMs, medical devices. You should know the capabilities, features, and uses of different types of computing systems like desktop computers, mobile computers, clusters. Be familiar with layers of abstraction from hardware up through software. The steps required to execute a computer program, fetch, decode, execute cycles. Trade-offs between local, network, and cloud computing and storage. And be familiar with communication between these devices. And again, so they put that in outline format, but then they also in that they put these questions here. So you should be able to, if you can successfully answer these questions, you're pretty good with computing systems part A. Okay. So think about that as you're, after this is over, as you're deciding when you're about to take the exam and reviewing a little bit more on your own. Use those questions as a guide. So we're going to start with the systems within a computer. And of course, we'll just start with, well, what is a computer? This diagram you've seen before in these presentations. Well, a computer is a device that processes inputs, creates different outputs, and uses memory to help that processing, right? So we've seen that, and we're going to look at sort of, well, what are the different systems that enable that to happen? What's the hardware that enables the inputs to come in, and the process, the process CPU, central processing unit, and the memory, and how does the computer output different things? And we'll look at the same thing for software as well. And so with that, I'm going to hand it over to Deborah.
All right. So when we talk about computing systems, you saw computing systems and networking and cyber, they are all together. So these are not going to be divorced when you're learning them. They're going to be combined, but we have put them in chunks so that you are able to go through them and review. And again, these are slides where you will need a lot of knowing the terminology and application. So when we're talking about hardware, we all know that those are the physical things that you can see, you know, the printers, the mouse, the chip, the screen, those are your physical. And then your software is mainly your instructions that control the hardware and other applications. So there are different softwares that tell the computer, this is how you're going to boot up. And then once you boot up, these are apps that are going to work. So that is what the software is all about. Sometimes they do talk about firmware, and then firmware is the one that is in between the hardware and the software and all that. But we are not going to dwell too much on that, just in case you see that word. But it's not part of the vocabulary that they've asked you. So input and output and the CPU. So computing systems will receive input in many ways from the keyboard, the camera, the sensors, and voice. all sorts of other ways, and then they will store information and process that to produce some kind of input. Maybe it's a picture, maybe it's another application that's going to work. So, so you have all sorts of ways that outputs happen. So don't limit yourself to just a few that we're talking about here. And then we all know the central processing unit, that is the brain. That's where you have the fetch instructions, instructions from memory, how they're decoded, what they mean, and then they execute. And again, we'll see a little bit more about how that works because you're required to know that information. All right, so this is just a picture of what kind of hardwares we can say. So, and again, don't limit yourself to the ones outside. The motherboard and all the chips and all those other things in there, they are also part of your hardware, even though you're not seeing them. So just in case you got a question about that. So you have you have the memory, you have the graphic card, you have the RAM, you have all sorts of other things that you find, and that's just a good graphic for you to have a visual of what's happening inside your computer. Then now when we talk about software, this is what you're required to know. You need to know that operating systems are programs that control and coordinate instructions between the hardware and the software components, know and identify components of software and their functions. Every system has three basic types of software application. So you have the top layer, you have the drivers, you have the operating systems. So the application, drivers, and the operating systems. Those are mainly what every system, whether it's an iPad, whether it's a phone, whether it's a regular computer, those are the common components that you will see in a software. So mainly what you would find in a question on software would be things that what they interact. So for example, operating, that's fine, Nick, you're fine. Yeah, in operating system. Yeah, for example, the operating systems and the details of what is happening there. Operating systems, they manage all of computer software and the hardware, including the CPU, memory, the storage resources, making sure applications get what it needs, whether it's a click, it's a sensor, whatever it needs, so that it can perform what it needs to perform. So when it's doing, and it can perform single or multitasking or whatever. So operating system, you can have single or multi-users. So you have different kinds of ways that you can do this. And then the user interface and the kernel of the OS. And that again is where you'd find some of the language that we don't use as human. We're not using it. That's for your hardware. But the common operating system tasks that you should know is memory management, processing management, device management, file management, security. So we didn't talk about that much the utility software, your utilities like your antivirus and all that. Those are going to deal with your security. And then control over system performance and job accounting. So it's going to account what is going to happen, what can it slow this, can it make this one faster, error and detecting aids, coordinating between other software and users. So when you see in ETSA, know the components and the common operating system tasks, these are it. So a question could come related to this information. All right. And by the way, before we go, make sure you do know different kinds of operating system and the common ones. The common ones being Windows, iOS, Android, and Linux. So just know that, and know that just because here we use a lot of Apple, we think everybody has Apple, just know that Android is more used in the rest of the world than Apple. That's just a hint of something. All right. Let's go next.
Sure. So I have an Android phone and a Windows desktop. So I'm not an Apple person.
Me too.
I know. All right. This is specifically written into those information that Nick read to you. So the fetch, decode, and execute, you are required to know that. That is that is the fetch, decode, execute cycle. The instruction cycle, which is the cycle that the central processing unit follows from boot up until the computer shuts down. So executing a single instruction consists of a particular cycle of events. So you start with a fetch, Nick is your doodle. You start with the fetch, then you go to the decode, then you execute, then you store back in memory. So usually I would prefer it having this the fetch on where execute is, because that's where you start. But this is good too, because it shows we are on the level of the memory from RAM, where it's going to take the information. Then it's going to go here in the central unit, where it's going to be decoding. And that means what is decoding? Internally, the program has to do stuff like adding things. So that's what's going to happen over there. Then you're going to have execute. So then it's going to use the register, actually adding the information that you said. So you've got the information, I need to decode this, I need to add. So how do you add? You go into the arithmetic logic unit, the ALU, and that's where the actual calculations and all that, the math is happening. And then once you get that, you're going to have that solution stored somewhere so that we can see it. And now another software comes in to help us physically see. So all this happened internally. And then at the end, we see what is happening. All right. So, and by the way, they could ask you anywhere. They could ask you in a question how to group those. Nick, leave this alone. That's fine. Just leave it as it is. They could ask you to just name the cycle. They could ask you what is happening or what should happen before the other. They specifically say know this and know how they are grouped each other. All right. Thank you, Nick. Then we come to abstractions, and what we are asked to do is to be familiar with with computers as layers of abstractions from the hardware, where we have the logic gates. So the logic gates are this, the AND, the NAND, or the NOR, the XOR. You don't need to memorize this. You just need to know that the hardware is made up of logic gates, and if you ever look very closely into a chip, you'll see that they are actually drawn in there. They are not physically laying over there, but they are actually drawn into your chip. And then, so that's the layer from hardware. Then you have the software applications, know how to identify appropriate abstractions layer from hardware and software components. And note that the firmware is virtual. It's software specifically designed for a piece of hardware. And we'll have a diagram that I'll just give you a minute to look at in the next slide. And just take 5 minutes, look at it. Let me know if you have any questions. All right, anybody with a question before I go through it? All right, so here we are just showing you, you start from the lowest end where you have the transistors, then you have the electronic circuits, then you have your gates. Please don't worry about any gates and flip-flops, you know, nobody's gonna expect you to learn that. So if you're reading something and you start seeing things about flip-flops, just ignore that. Then, of course, then you have your chip, and then you have your integrated circuit, the motherboard, which is all these things make up a final motherboard. They are all in there, embedded into the motherboard for you. So binary data is processed by physical layers of the hardware. They use by a machine language, which is your zeros and ones. And the way we go through it, again, we have the lowest of the lowest level. Of course, we have the hardware. The hardware alone can do nothing. So it has the the firmware, where then it's going to use the firmware to communicate. And then you have the assembler, so the firmware more of your binary and all that. And assembler is also some binary and some English. So you have that. Then you have the kernel of the operating systems, and then you have your OS. You have the kernel where the operating system is working. Then you have your OS again and your applications. So all this happens without you knowing, and all we get to see is the top layer. That's what most of us are always working with. We are always working with the top layer, other than students who are doing networking and sometimes students who are doing cybersecurity, and you will hear quite a bit and maybe some repeat of the same information from our guest speaker, Kim. Right. And I hope you all know Kim. We'll introduce her a little bit later, but she was here talking with some of you. All right, Nick, let's go next.
Okay.
We'll hand it over to you.
Yep. So we're just going to talk very briefly about some of these multi-computer systems that you need to know about. But I'll stop short of going into networks, because then that will be its own presentation in a little bit. So some of the multi-computer systems, well, all of them rely on communication between computers. So just as like a little prelude to networking, some understanding about how do computers even communicate, right? So they can communicate wired, right, through the Ethernet protocol, which most of you may be using right now. If you're at a desktop computer and you have an Ethernet cable plugged in, well, there's also a protocol associated with how messages get sent over that Ethernet cord cable. Or phone and using wireless communication and the protocols associated with that right now. As the physical level, of course, that was talking about the protocols of how do messages get sent, how do we interpret those ones and zeros. Well, if you go a layer lower to the physical layer, then we're talking about what is actually connecting them. So for example, the coaxial cable, like the copper wires and how they're twisted, or the fiber optics if you're on a FiOS type of system, and the glass, thin glass threads that send light from one end to the other, or the radio waves if you're on Wi-Fi, right? That's all communicated over the radio through the air, or communicating through cellular networks, right? And the cell towers, or through communication satellites like GPS, right? So computers communicate with one another in all of these different ways, and more info on networks can be found in the next slide deck that you'll be seeing and presented on later on. So all multi-computer systems involve some sort of communication. So one of the talk about the Internet of Things, and so I mean that's sort of a newer name for it. Earlier, the same thing or similar would have been called sensor embedded systems, right? So if you think about smart homes, for example, if your smart TV, right, can connect to the internet and you can play YouTube or Netflix on your TV, right? Or your smart refrigerator. I don't know if any of you has a smart refrigerator. I've only read about them in stories. I haven't seen an actual one, but a smart refrigerator that can like look at what's inside of itself and tell you what you need to buy because you're running low on eggs. So put that on your virtual shopping list and send you a ping when you enter the grocery store. Or a smart home, like the cameras at the front of the door that you can access from an app from far away and see if somebody rings your doorbell when you're not home, or the or any of the smart home assistants that you hear about, Alexa or Siri or Google Home, or what Facebook Portal is trying to get into that area too. Anyway, so smart homes are part of the Internet of Things. Basically, the Internet of Things is anything that's not a traditional computer that has been connected to the internet, right? So a refrigerator traditionally is not a computer, but now they have refrigerators with computers built in that do connect to the internet to do those things, or a smart toaster or a smart coffee maker that will make you coffee every morning without, you put the ingredients in the night before and it starts brewing at the right time in the morning and sends a ding to your cell phone when it's done, right? Anything that is not traditionally part of the internet or not a traditional computer that has been connected to the internet, usually through sensors, is part of the Internet of Things. So smart homes are of course, a smart curtain rod. What is that? I've never heard of that before.
The smart what?
I have a 15-foot sliding glass door in the front of my living room, and so I can now tell my phone, I can be like, okay, Google, open the curtains, and it opens the curtains.
Oh my God.
No, don't actually open the curtains. Sorry, my phone is here.
Oh, it was listening
yeah.
to you. Oh my gosh.
Okay, that was awesome.
Wow.
That was good.
So
Just in time, it's in real life. And you know, with all this, that's why we are going to want to have Kim, because guess what? Some companies are making them all very well connected, but how secure are they doing? Kim will let us know.
Yes, I will. Yep, we're talking about that now.
Who can hack your smart
curtains.
and
It'll just drive you
back
crazy.
and forth at you.
As I was going to say,
or, yeah.
that'd be a great like April Fool's Day joke to people. Just go back and forth. It's really irritating. Thank you, Heather, for the idea.
Ooh, does that mean you're actually going to hack hers right now and do that? So the Internet of Things also includes, of course, things that are like wearables, like your Fitbits or smartwatches, or it was Apple Watch is the brand, or I don't know. I think Google Glasses never really took off, but that would be considered a wearable, right? Google Glass. But it also sometimes people don't think of as much would be the connected infrastructure, like smart cities, right? So any sort of like if you have traffic lights that are connected to sensors in the ground and monitoring how much traffic is going through, so that they can adapt sort of on the fly about how long the red light is or green light is depending on the traffic, instead of being just on a simple timer. That could be part of the Internet of Things if you have that in your city. Or connection to buses that are connected to the transit app, so you can know when the next bus is arriving at your stop, right? Anything that's part of that connected infrastructure for smart cities can also be part of the Internet of Things or sensor embedded systems. And industrial control systems are also part of that as well. And that can be like a factory line where there are thousands of sensors at various points, making sure that the parts are flowing correctly along the assembly line and no backups at any point. And then all of the robots that are connected to it, all the robot arms are working correctly together, and all of that is part of the Internet of Things as well. As a little tidbit, if you ever wanted to know the first thing that was connected to the internet, a non-traditional computer, was actually a sensor hooked up to a soda machine, Coke machine, at Carnegie Mellon University in I think it was the 1970s. Back when the internet was still much in its infancy. And so they hooked up a sensor to see, well, was the soda machine full, or was their favorite soda full? Was the Coke full? Was the Sprite full? Right. Because these were computer scientists, of course, working in the computer science department at CMU, and they were lazy. They didn't want to get up from their desk and walk over to the Coke machine only to find that it was out of Dr. Pepper or whatever their favorite was, or to find, or possibly even worse, to find that it was full, but somebody had just restocked it like 15 minutes ago, and so it was all warm. It hadn't been cooled down by the refrigerator yet. So they had a timer connected as well as a sensor connected to see how full each section was, and they would just use their internet protocols to ping that and see before they would walk down the hall and go get a soda.
That's awesome. That's laziness is the mother of invention for geeks.
Yes.
Sorry, guys, but
Yes, it is.
Totally. Yeah. And I teach that to my students all the time. Is computer science. If you're lazy, just write something in code for you. Now, yes, that might take a lot of work at the front of doing the code, but eventually it'll allow you to be.
Virtualization. How do you think it came into remote? There you go. We don't want to get up and go anywhere. So sorry.
So I think this is the last slide is about the cloud as another system of multiple computers. And the cloud, I've got this sort of picture over here, is actually just a computer somewhere else, right? Or a server somewhere else that is storing your data. And the cloud can be used to store data, as it commonly is, but also run whole applications can be run on the cloud, right? So like Google Docs, right, or Google Slides that we're in right now is a cloud application that their software is running server side over there and allowing me to type in this presentation and now to present it to you, right? And it is also the computing infrastructure is all those things, the data, the applications, and or the computing infrastructure is all on a faraway computer somewhere, maybe in Utah, in Google's or California and Google's servers maybe. The cloud can be used as a backup to local storage so that if you lose all your information due to a hurricane or something, you still have a backup stored on the cloud. Or it can be used instead of local storage. A lot more and more people are storing stuff on the cloud only and not saving another copy to their hard drive. And you should be able to think about those trade-offs, right? Remember when I mentioned in the outline, trade-offs was one of the things mentioned that you need to be able to think about for all of these things, right? So what are some advantages and disadvantages to the cloud? So some of the advantages can include accessing your data anywhere. So I can access my Google Slides from my desktop computer. I can access them from my phone. I can access them on my tablet when I'm far away from my house, right? From my school. You can access them anywhere, anytime. You can also use them to back up your data so that it is not lost, as we mentioned, due to a computer malfunction or due to maybe a hacker comes and ransomwares your computer. Well, you backed up your data on the cloud, so at least you still have a copy. Now, you might not still be happy with them, but you still have your own copy. And another advantage is with the cloud, you can collaborate with others more seamlessly than you could before when you would store local copies and email each other and say, this is version 1 of the document, version 2 of the document, version 3 of the document, version 4 final, version 4 final, 5 final, right? If you would email and collaborate back and forth with each other without the cloud, it was a little bit tougher, okay? Some disadvantages, of course, are that you have less control. You have less control over your data and potentially it's less secure. That, of course, companies try to make sure about cybersecurity, but there are more entry points to be between you. It could be in transit between you and the cloud that a hacker could get in, or it could be on their server out in the cloud that a hacker could get in. So potentially it could be less secure. And it requires those intermediate steps that happen through your browser or through your apps. So we'd like to take a couple of minutes and we'll do breakout rooms, even though there's only 2 questions. But just to get you all up and talking and awake this morning, we're going to just take 5 minutes in breakout rooms. And please just look at these 2 questions, discuss your answers, and then we'll be back in 5 minutes. Continue recording and share my screen again. So let's just look at those 2 questions. You can say it out loud or type in the chat. What did you answer for number 22? Which of the following is an example of the use of a device on the Internet of Things?
My group initially thought it was all of them, but then we realized that it had to be connected to the internet.
Yes, very, very good point. And I'm seeing the
That
answer in
is
the
the
chat.
key.
Yeah.
Yeah.
So they did purposely make it like that. So all of those things are examples of technology that could be connected to the internet, right? So oftentimes you have cars that are connected to the internet. But if it's just alerting the driver, not alerting like the police or what is it, not on shape, but on board on something. So whatever system that like alerts authorities or alerts if there's crash.
The radar detector.
Maybe, yeah. I'm thinking of a company name, but could be, yeah.
Oh.
But if it's just alerting the driver, no.
Okay.
OnStar, that's it. Yes, I knew it was on something.
OnStar. Oh.
And I use OnShape with my engineering students, so that's what first came to mind. But if it's just alerting the driver that it's about to hit something, all it needs is the sensor inside the car and the computer inside the car. It doesn't. Same thing. So GPS is actually a separate system from the internet itself, but it is being connected to satellites, right? So sometimes people think about that with the internet, and oftentimes it's paired with something with the internet. But again, if it's just the GPS, then that is not part of the Internet of Things.
Yep.
A refrigerator or a runner using a watch with optical sensors to monitor your heart rate. Again, if it just has those sensors and you're only monitoring it for yourself, not connected to the internet, that's not part of the Internet of Things. But oftentimes people do pair that and maybe have their app tweeted out or somehow be a social aspect of heart rate and stuff like that, or map your route and display your map on whatever social media. So oftentimes, so they did purposely make this a little bit tricky, but yes, the key was C. A refrigerator orders milk from the online delivery service when it is almost done. As the online delivery service and the ordering itself is the key there. Okay, how about for number 23? Yes, that is exactly what a compiler does. Is it takes a high-level language like Java, for example, and it translates it into machine code or the ones and zeros that the hardware can actually run.
Nick, excuse me, doesn't it also check for errors though?
Yep.
Yeah.
Okay.
But that wasn't any of the options, was it?
Oh, B said, what does B say? I can't read it.
Okay. Yeah. So I get how you might have thought that. So testing the software, that checking for errors. But the keywords here is about in the process of developing executable software, right? What is the actual thing that can execute? And no,
Yeah.
the compiler does not test the executable, right? The compiler checks for errors before it creates the executable piece that can be run on the computer. It's sort of a pre, right? When you're compiling it, it's pre-creating that executable. And instead, it actually tests it before, and then, or checks it for simple errors. Not every type of error can be caught by a compiler, but yep. And then what it actually does is it translates the program. Yep. So good point. Some other people might be confused by that as well.
Yeah, so it's, and also just know when you're being asked for one answer or when you're asked for more than one. But even if they had said two, the B still would not be a process of developing an executable software. So that the language, the vocabulary, almost all these questions, it's the vocabulary. So as you go through your practice question, look at what the words mean and the choices, because that's what it comes down to.